Today we are going to look at a structural analysis of a single rigid body in 3D. You have seen several examples where we did this thing in 2D. Today we are going to see how to do this kind of thing in 3D. Just to get you an idea, there is nothing new in this. We have already done all of this kind of stuff. So the higher order thinking skill, remember HOTS means higher order thinking skills. The higher order thinking skills is the following. It's the same as 2D. There is no difference. So actually there is less trig, so it's easier. The main thing is you should be able to find the force vectors, and we have to create a force table with more things. So as usual we have point. Now instead of just x and y, we have x, y, z. That creates the position vector, and then fx, fy, fz, which creates the force vector. And instead of having one moment, we have three moment vectors. Mx is yfz minus zfy, my is zfx minus xfz, and mz is xfy minus yfz. And then there might be this additional term is things that we saw when we did built-in joints and things like that, where there might be some concentrated moments. So we just create this force and moment table, and summation of all of these things will give you 6 equations. Can you see the 6 arrows? So if I sum all the tables, I will get 6 equations. And of course you can be clever and do all kinds of things, but the basic idea is identical. So it's not a big deal. So let's get started. So here is the problem statement. So I have a crate which is hung from 3 cables. Can you see that? AB, that's this cable, AC, that's this cable, and AD, that's that cable. And what we know is that max load on the cables has to be 100 pounds. So the question is, how much is the load on the crate? How much can we take? How big of a crate can we use with this set of 3 cables? By the way, if you look at this sounds like a kind of a silly problem, but it's actually not. This is the foundation for how many cranes and things are designed. So this will be what is usually called the support wire, so that you move the cable, you can move the weight around, and these will be the main wires for a crane system. And the crate is actually one of these big crates that you use to load ships and things like that. So it's actually a simplified version of a much more serious problem. Okay, so our high level strategy is the following. What we want to do is find out what's the max allowable load. So what we will do is we will see per unit pound here, how is the load on this shared by these 3 things? That's the question. So each pound of the crate load, how is it handled by the 3 cables? That's what we're going to find. And then we will find which is the cable which is having the highest share. And then we will scale up the load until the cable with the highest share leads 100 pounds, because all the others will have a slightly lower share, and then we will be ready to do. You got that, right? So that's the strategy. Let's see the implementation. So how are we going to do it? We start out by assuming that the crate weighs 1 pound, and then we calculate the load on all the cables. So this will allow us to tell us how much load is carried per pound, and then we find the cable with the highest load. This is easy, just look at whichever is the highest number, and then we scale it until the load on that cable reaches 100 pounds. So let's see how we do that. So first step is to draw the free body diagram of the joint A. Why do I want that joint? So this is, remember, this is the free body diagram business. I need to figure out which body to isolate, and I'm going to isolate the connection. Why do I isolate the connection? Because that will reveal the 3 forces that I'm interested in. This we already know. This is the crate load, and we got to look at these 3. So I'm going to draw this free body diagram here, and I'm going to have 3 forces. F, and this will be called AB, going that way, and then F, AC going that way. That's this one, and then F, AD going that way, and then W crate, which is equal to 1 pound. And my coordinate system is going to be Z, Y, x. Right? You got the idea, right? So now we have to find these forces. Let's look at the point A. That's our origin, 0, 0, 0. That's A. So I'm going to write it out. A is 0, 0, 0. B is, let's see, x component is minus 3. Y component is, let's see, minus 4. And z component is 8. C, x component minus 3, y component plus 4, z component 8. And then D, x component, let's see, we don't care, we don't know, but something x, y component is 0, z component is 0. Notice this, I don't really need to know that because we can now compute all these unit vectors. So I need to find EAB, EAC, EAD. We're going to do that next. Okay, these are our components. So let's get there and see how we do it. Here was our free body diagram: FAB, FAC, FAD, W. Let's see. FAB equals, remember this is a vector, equals magnitude, that's FAB, times line vector over line length. We know how to compute that, right? So we will do it for all three of them. FAB, magnitude unknown, line vector is minus 3, minus 4, 8. This is the line AB, divided by line length is square root of 9 plus 16 plus 64. That turns out to be FAB times minus 0.318 plus 0.424, 0.848. Check the numbers, but you can see x component has to be negative because it's pointing along the negative x direction. Y component has to be negative, so my sign was wrong. This is negative because it's in the negative y direction. Z component is positive. So please make sure, first thing to do whenever you do some calculation is to check the sign. Notice this sign has to be the same as that sign. Okay, let's do FAC, and that should be easy. If you do the same thing for FAC, you will get FAC is the force and the magnitude is minus 0.318, 0.424, 0.848. And then FAD, again we don't know the magnitude, but we know its direction. It's 1 in the x direction, 0, 0. You remember, we didn't know actually how far this was. We didn't know, but yet we could find the unit vector because anyway we divided it by the number. So it doesn't matter what the number was. And then the last force, so we did this. Usually as soon as I write down one of the force vector, I put a tick so that I made sure that I have calculated all of them. So here's a tick, here's a tick, here's a tick, here's a tick. Oh, I have not done that yet. W, the crate load is 1 pound in the direction 0, minus 1, 0. Can you see that? So that's it. So off we go and we are ready to create the force table. So in this particular case, our force table is pretty easy because all the moments are 0. Because all the forces go through 0, 0, 0. So in fact, that's one of the nice advantages. If all the forces pass through the same point, no need to check moments. So I don't even have to list all the forces, but I don't even have to list all the positions because all the positions are known. I'm just going to list the forces again. FAD was unknown force times minus 0.318 minus 0.424 and 0.848. The next one, FAC equals FAC, again I don't know. So remember, this is FAD vector, this is magnitude, and this is direction. The next one is minus 0.318, 0.424, 0.848, and then FAD equals FAD unknown 1, 0, 0, and then W equals 1 pound 0 minus 1 0, sorry 0 0 minus 1. It's in the Z direction. So now we are going to use Newton's laws, which say sum of all the forces must be equal to 0. That means if I add all the x forces, this and that should give me 0. This, that, this should be giving me 0. This and that should be giving 0. So what happens is I will get three equations. FAD, sorry, let me write it down right. So let me write these things down properly. Zero, 0, minus 1. In the previous page, I had written 0, minus 1, 0. So that's not correct. This is the correct one. Summation of all the forces equal to 0 gives me minus 0.318 FAD minus 0.318 FAC, sorry, FAB, plus FAD equal to 0 minus 0.424 FAC minus plus 0.424 FAD equal to 0. Then the last one gives 0.848 FAC, sorry, FAB I got to be careful about this, no? So this is B, that's C. Notice I always make mistakes on this, but I want you to understand that that's actually common, and so it's important to check these equations before you proceed. So check and check and check and check and check, and that's where most of the mistakes show up. So please pay attention. 0.848 FAC minus 1 equal to 0. So how do you solve this? This is equation 1, this is equation 2, this is equation 3. You can use your calculator, you can do whatever you want, bring your supercomputer to class if you want. The important thing is to be able to solve this. You will find that 2 will give me, I'm going to solve this and it will turn out. So why did I stop? I want you to remember something. It's no point in just watching me. I am hoping that you took a paper and pencil and you are calculating all of these things along with me. Otherwise, you will not know what it is. So what I want you to do is now pause, write down these three equations, and then you will see how I solved it. Okay? So did you pause? Did you write down these three equations? Very good. So I'm going to go ahead and go to the next one. I'm going to go ahead, go to the next one. So here it is. Solve it and scale it. So we're going to solve it first, and the solution looks like equation 2 will gives me FAB equal to FAC. Then substitute into 3 and you will get FAB equal to FAC equal to 0.590 pounds for every pound of crate load. And then FAD equal to 0.636 FAB, which turns out to be 0.375 pounds per pound of crate load. Notice that yes, the forces in the cables are less than the crate load, but they are not. The sum of all the forces doesn't equal to the crate load because of the angles. You see what I mean? But you notice that FAB and FAC carry much higher load than FAD. It's only 60% of the load. You see what I mean? So this is the critical cable. So now let us see how to scale. Of course, I'm going to do this in a kind of a painful way because I want you to follow. So how do I scale this? 1 pound crate will give me 0.590 pounds FAB. Right? So how much will 2 pounds give me? Will give me 2 times 0.590. So how much will X pounds give me? Will give me X times 0.590. So how much can X be? X times 590 must be less than or equal to 100 pounds. So X must be less than or equal to 100 pounds divided by 0.590, which is approximately, so that I get the right number, is 169 pounds. So max crate load equals 169 pounds. Thank you very much. I hope you followed it. So the basic idea is, core idea summary, is for max load problems, assume load equal to 1 pound and find how it is shared. Find the component that takes the biggest share scale it until, in fact this step depends. So if, for example, if there's a particularly weak cable, even though it's not taking the biggest share, it may fail. So let us not really write it this way. We'll say scale it until one of the cables becomes critical. May not necessarily be the cable with the biggest share. It may be a cable which is the weakest. Okay? Thank you very much.